So my name is Alban. I'm in Berlin. I work at Kinvolk. I love Linux and BPF. And at Kinvolk, we care about Kubernetes and low-level Linux development, things like BPF as well. I will start. I will not introduce too much eBPF. How many of you know about eBPF? Okay, almost everybody. I will just introduce it quickly, and then I will go to a few demos, and then I will explain how things work. So if I just say a few words of eBPF, that's like small programs that run inside the Linux kernel, and that can be used for security, for tracing, or networking. In this talk, I will focus only on tracing, so how to trace your Kubernetes cluster using BPF. And I will talk about concepts like kprob, uprob, UDSD, and tracepoints. Using eBPF is safe. If I compare to running other things in the Linux kernel, like kernel modules, it's not like that. It's safe. It will not crash your kernels. And it's safe because there are restrictions about what you can do. And in the kernel, there is a verifier that will verify that your eBPF program will not run indefinitely or do unauthorized access to some memory or so on. And it's safe as well because BPF is a bytecode, but it will be compiled to native code, and then that will run as fast as doing a normal function call in the kernel. If you want to learn more about BPF, that's a good pointer to look at, the BCC project for BPF compiler collection. And if you use Go, you can look at Go BPF as well. So I will start first demo. This is about bpftrace. bpftrace is not, it's a tool that runs on one node. You can start from the command line and you can type a one-liner small BPF program. So it has its own language that you can type on the command line. It will be compiled on running on the node. So this is not a cluster aware or anything, and I will prepare a demo. Bigger? Is it good enough? So here I have, okay, this one is not exactly a one-liner, but it's a small bpftrace program. What it does, it will use a uprob to trace in the other bash process. Every time you type a command in bash, it will capture the function readline, and it will print the return value of readline. So that's the command. So if I start this program, so far nothing happened, but I go to another terminal, and I type some command. Yeah, okay. That was some commands. And here I see the results. So it says every command I type here are captured by bpftrace. It does that on all the processes on the system that run bash. It puts a uprob on the specific function in the bash binary and capture that. So the idea of kubectl trace is to do similar kind of things, but on a cluster level rather than on a single node. So now we'll do the second demo on kubectl trace, and for that I have a bit more complex setup. I have a Kubernetes installation. I use Flatcar Linux as a base Linux distribution that we do at Kinvolk. I use a Kubernetes distribution based on Typhoon with a special image to have the latest Linux kernel because I need some BPF function in the latest Linux kernel. And I will do a demo with a microservice application that was developed by two companies, Container Solution and Weaveworks. So I will show you right now how does this application look like. So the application is, it is a web app where you can buy socks or pretend to buy socks and click on different articles you can buy. And this is running on Kubernetes. So let me stop that. Sorry. So I have a Kubernetes cluster with a namespace for this application, and I have about a dozen of different containers. And here I want to trace what happened in one specific container, the front end. Before this talk, I prepared a few environment variables. So I have the pod environment variable that I want to trace is running on this node under a C group, which is listed here. And now I will copy paste the command I prepared before. This one. What it does is I use kubectl trace and I specify on which node I will run that, and it will attach to the a kernel function with a kprobe. The kernel function is do sysopen, so every time the system call open is called, the BPF program will be executed. And the BPF program will do something like printf and print the program name and the first argument of the system call open. So I have a Node.js application, so the name of the program is Node, and the file it's open is it's opening some file, but nothing important so far. And here I don't want to trace all the process on the system, but only the process that run on a specific pod. So I added a filter here. That's something you can do with bpftrace. Here I say I only want to print the trace whenever. Oh, it's gone. I will show you. Let me stop that. I only show the trace when the current C group is the one of the container. So now I start this again. And if I go to the Firefox and I refresh this page, here I see it has a lot more file that it has open. So the node running in a container has opened a lot of files. So that's it for this demo. Thanks. So to sum up, with kubectl trace, you can deploy pod with bpftrace and inspect some pods with bpf. So that was in case network was not working, but the network is working here, so that's the same thing. So how does it work? So kubectl trace is a client-side plugin to kubectl, so it doesn't run on the Kubernetes cluster, but it runs on my laptop. So when I type kubectl trace, it executes the plugin, and this plugin will not do any SSH to the server or anything like that. It only uses Kubernetes primitives. It will create Kubernetes native resources like config map or job or pod or things like that. So the first thing it does is it creates a config map with the content of the program. Okay. It creates a job that will be deployed on a worker node. The job is a trace runner pod that will run bpftrace. And that thing will install the BPF program. So I will zoom in on that pod here to see what it does. So this process will fetch information from the config map to get the program code. It will get the kernel headers from the host and compile it into BPF bytecode. It uses LLVM to do that. And then it will install the BPF program in the kernel with a BPF system call. With the BPF system call, we get a file descriptor and representing the program. And then we attach that program to specific hooks to specific points with kprobes or uprob and so on with a tracefs file system. And a lot of this is done with libbcc. To be able to do that on a Kubernetes cluster, we need a lot of privilege. For example, we need capsysadmin because a lot of BPF operations need this privilege. We need to have access to some volumes, like for example the tracefs volume, or to get access to the kernel headers. So in Kubernetes, we actually use some pod options like privilege equal true, using the volumes and so on. If your Kubernetes cluster is configured to use pod security policies, you need to be careful to configure that correctly. So you need to configure a service account on cluster roles and so on. So that's the usual airbag things, role-based access control. With kubectl trace, you can do different kind of tracing in kernel or in userland. In kernel, you can do trace print, that's statically defined trace print that are defined in the Linux source code, or kprobes, which are more dynamic. You can give any kernel function and put a trace print, a trace on that. Or in users program, you can use UDST or uprobe. Trace print work like that. They are statically defined, and at the beginning of a function of this code, you might have a trace print that is executed or not, depending if there is a trace print at the moment installed, and then it will execute the BPF program that will emit some events. Kprobe is very similar, but the code is patched at runtime. So you can do that on any function. It will replace the first instruction by a jump, save some register, do the call to the BPF program, and then return after having executing the original instruction. User level statically defined tracing. That's something, here I give an example how to know if one of your programs do that. You can use the readelf command with -n, and you can see some trace defined here. On uprobe, that's the demo that I did before with to read the command line from another process, from bash. So that's the 4 main things you can do. So when preparing this demo, I had my biggest challenge was how to do this filter here. So if I show again, how do I do this filter? So this was not implemented at the beginning, and I implemented that in bpftrace and in kubectl trace. So to select the pod, the issue is that BPF programs are installed in the kernel and are global. They are not installed for a specific PID or cgroup or container, but they run globally. So I need a way in the BPF program to check what is the current context. So I look at the list of BPF helper functions, and some of them are going to help us. So this one get the name of the program with a com short name of the program. That's not really so useful because you can have that on multiple programs and that's easily changeable. The most interesting thing is the cgroup ID, which is in the last recent kernel version. So looking at the documentation of that, it returns a 64-bit integer giving the cgroup ID. So based on that, I did an implementation in bpftrace, in the language specific to bpftrace, to have a built-in cgroup that returns the current cgroup ID based on this BPF helper function. And then another built-in cgroup ID that does the translation of, you give a path of a cgroup, and it returns that. Another issue is in the kernel, we have 2 versions of cgroup version 1 and cgroup version 2. And yes, so both can exist at the same time if you select both, but that's a bit complicated to manage. The BPF helper function only care about cgroup version 2. So the problem is Kubernetes normally use only cgroup version 1, so I needed to do some change there. So first I configured systemd on the host to use both version 1 and version 2 with those parameters. And then there is a configuration in Docker to say, don't do cgroup yourself, but ask systemd to do it. And then, because systemd is configured to do both version 1 and 2, it will do that. And there are similar options you can give to the kubelet and to containerd. So after doing that, the container will run with version 1 and 2 at the same time. That's how I could filter on the pod with a cgroup version 2 ID. So to finish this talk, I will give just 3 short ideas about things I would like to have in the future in this project that maybe I could implement or you can implement. First, to improve the user interface, because the way I did it here, I give the node environment variable, I give the cgroup full path. Ideally, there will be a way for kubectl trace to get that automatically. So that should not be too complicated to implement this kind of automation. Another idea is to have aggregation. So usually when we do deployment of on Kubernetes, we have several replicas, different pods, running potentially on different nodes. And it would be good to gather the result of those different pods and aggregate the result on tokens. And to finish, so at the moment, kubectl trace needs to have privilege on a cluster, but sometimes it's not that good that every user have complete access to the cluster. It would be nice if a user could inspect their own pod without being admin on this cluster. So that's an idea, but without clear idea how to implement that, that will require a lot of thinking, I think. Okay, thank you. Is there any question?
Got time for a couple of questions if there are any.
Great talk, thanks. Do you need the kernel headers to run bpftrace?
Yes, so I think it depends what kind of prop you do. If you use kprops, yes, you need kernel headers to know what things you inspect in the kernel. With traceprint, I'm not sure. I think it should be possible without, but I've not tested.
Anything else? Doesn't look like it. Thank you.